So my name is Skylar Eldridge. I'm a postdoc at IBM TJ Watson. And the first thing is usually why am I talking in the software section? Usually I'm always just talking about Chisel or Fertile. But what I'm presenting today sort of on behalf of Ramon Bertrand and myself is talking about a micro-benchmark generator called Microprobe, which IBM for a while has used internally to evaluate power and System Z microprocessors. And then we led a port of this to the RISC-V ISA, and we'd like to make it available soon. This is intended to be open sourced with an asterisk in the sense that this is currently held up in some legal review, but we're intending to get it out and make it available for anyone that's building RISC-V implementations. So what is sort of the high-level reason for why people want to make micro benchmarks? So obviously, it's normally you have some high-level question about the interactions of the architecture, the microarchitecture, the environment, and you'd like to then be able to verify that you have a good design. And that means being able to answer questions like, what is the actual power consumption of my design? It has some TDP, but what is the worst-case power consumption that we can actually expect? Are there any performance bugs, odd ways that instructions are interacting with each other? Or is my design reliable? And this list goes on and on and on. So the unfortunate thing is sort of before Microprobe at IBM, the way that this would be done is that you would have individual designers and really specifically architects, which would then have to go and then write their own micro benchmarks. And the real problem with this is that in order to write these very weird interacting micro benchmarks involving the caches, the architecture, the microarchitecture, that you really need to have very high-level semantic information. Basically, you need to be an architect. So what this is trying to do is to then develop a workflow such that then any design verification engineer is then able to then go and then for a question that they might have, like one of these, they're able to then emit a micro benchmark that's able to attack that question. So what is Microprobe? So first, it's a micro bench. It's intended to probe or to automatically generate micro benchmarks. It's not an electrical probe or anything like that. But it's specifically a code generation framework that is enabling you to answer microarchitectural, architectural, and environment questions that you may have. And as I mentioned, this is the internal tool for IBM Power and IBM Z systems, and primarily led by Ramon Bertrand, who's not here today, but would be happy to answer any questions that you have about this via email. So it's easier to walk through this with sort of a user story. So you have a designer here, sort of with the caricature on the left, and they're saying that I would like to then like to be able to generate a micro benchmark that's able to generate a loop for each instruction. Okay, well that's relatively easy, but what about for a given instruction distribution? Okay, you could do that. What about with certain memory activity? And then sort of internal to my group, where we're more focused on low power designs, how can we create a loop of instructions for generating inductive noise at a given resonant frequency? So this is really trying to say that this is intended to be a tool that's used for answering these types of difficult questions or developing tools to help you answer these types of questions that are really difficult or would require you to go off and talk to the actual architect and get their valuable time to then try and help you with this problem. So the way this whole thing works at a high level is that a user is then responsible for writing micro benchmark generation policies. And what this really is there's sort of an intermediate representation for describing benchmarks or types of operations on benchmarks, and then you write passes over this. That then gets passed into the Microprobe framework, and then on the other side, you're able to get whatever sort of backend you want. It could be a C program, it could be some raw assembly, it could be an actual binary. Now, obviously, in order to do this in a generic way, it's difficult, but using standard software engineering practices, you're able to come up with a way of doing this that Ramon was able to drive through. And basically, his observation is that you can decouple everything related to the target definition, so everything related to the architecture. So in this case, the specific things related to the RISC-V ISA, everything related to the microarchitecture, so something like the specific details of your rocket ship configuration or your Pulpino configuration, and then additionally with the environment, and those are all separate things. Those are then all described using not a markup language called YAML. And then from there, then code generation is then handled directly using Python, and then the generation policies, which the user is expected to write, are then also written in Python. So in order for just a basic RISC-V port, which is sort of what we've provided here, all that you really have to do is come up with a way of describing what the RISC-V architecture looks like in sort of a YAML format that Microprobe is then able to understand. So obviously, in order to do this, the one thing which would have helped immensely is if there was a machine-readable specification of the RISC-V ISA. So this is something which we would be happy to have more discussions about what this would look like, and there do exist certain sort of things moving in this direction currently, which I'll talk about. So just how this works, so everything in Microprobe is sort of related into a box, and everything sort of external is outside. So towards a machine-readable specification, so Michael Clark has an emulator called RV8, which sort of subsumed a repository called RISC-V Meta, which is sort of, if you're familiar with the structure of these different repositories, there's just a RISC-V opcodes repository, and then RISC-V Meta is sort of expounds out on all of the different things which aren't specifically discussed in RISC-V opcodes. What we're able to do is we directly parse that, and then use that to then generate our RISC-V ISA target definition. And I'll get into a little bit more detail on what all these individual files then represent. But roughly, once we then provide all of this for you, then as a user, then all you have to do is write your generation policies. So in terms of just expounding out on what that RISC-V ISA definition looks like, so a collection of different YAML files. So in this case, you have something which is describing what every instruction looks like. There's some sort of mangling on the end of this, which is more of an internal thing for us. But basically, you have something like an add instruction that is an R-type instruction. All R-type instructions have different instruction fields. In this case, you have source registers, destination registers. And then from there, those then consist of specific operands. So this is sort of like things which are going to come in and you're going to bind when you're going to generate these benchmarks. So in this case, an operand is a register. Registers then can be of different types. You can have integer registers, floating point registers, which is then sort of shown here. So basically, we provide all of this for you. And then going through with that, then you're able to then, with this provided, then use Microprobe and as an example here of what the type of question that you can ask. So as I mentioned previously, this is the rough structure here is that we use an intermediate representation of tests, of micro benchmarks. And what we're trying to do here is to decouple the actual micro benchmark description at a high level from the actual code generation that's associated at the back end. And for that reason, then we're then able to say that we don't really care what the back end, if it's assembly, if it's a C program, if it's a raw binary, we don't really care. We're decoupled from all of that. And then we allow the designer, so in other words, verification teams, to then live at this level of just writing what the micro benchmark description is and leaving the rest of the hard, heavy lifting to Microprobe. So alternatively, then you think about this as a user approach to code generation, where as one example, generation policy is written as in terms of a sequence of compiler-like passes. So in this case, then sort of for this one generation policy, and I'll go into a little in more detail with an example on the next slide, but what you can then do is then you can operate at the level of, well, I would like to have a building block of some number of instructions. I would then like to fill that building block with instructions that are only going to target the functional units that I care about. Say, let's go and bang on the floating point unit. And then all instructions should access memory, but they should only ever hit the L1 cache. Okay? And then finally, then you can set operands to provide either specific instruction dependency distances. So these are your relationship of read after write dependencies. Or you can say, I'd like to completely avoid any dependencies so that we can run this thing as fast as we can. So in that case, what this is really sort of structured here is this is sort of a micro benchmark which is exercised in the L1 cache, and it's also exercised in the floating point unit, and it's trying to run as fast as it can without any kind of dependencies. So now a little bit of a more concrete example, and with sort of a hello world style experiment of something you can do with this is, so what I'm doing as a user of Microprobe, I'm starting with a question. And what I would like to do is I'm asking, so what are all of the individual latencies of different functional units in Rocket? Okay, or alternatively, can I, from the outside, reverse engineer the internal Rocket implementation just using Microprobe? So then as a user, then what I do is I say, okay, so the way that I'm going to do this is I want a microbenchmark which is going to loop over all the instructions that I care about with different dependency distances, okay? So in other words, something which is then going to allow me to extract the throughputs and the latencies of all of my instructions. So then what I do here is then Microprobe then emits your benchmarks for you. You then run the benchmarks on whatever your platform is. In this case, it would be the Rocket chip emulator, or it could be on FPGA. And then you interpret the results to then answer the question that you started with back at bullet 1. So I realize code is always not the best thing, but I find that this is somewhat useful because it shows sort of the simplicity of what you're able to do as a user here. So in this case, you start off with, you need to have some definition of what you care about. So it's these 3 things that I mentioned before. You have a target, so you have that encompasses a target. So in this case, you have the ISA. So this is a specific version of the RISC-V ISA. Then you have an architecture. In this case, it's just a generic microarchitecture. And then finally, you have an environment. So this case, it's Linux GCC. So then from there, then I define the instructions which I specifically care about and define some variables in Python. And basically what I'm doing is I'm reserving some registers saying that I don't want to mess with the stack pointer and all that kind of thing so that this is not going to cause my system to crash. And then I define that I want to generate a C program that is going to then loop over this. In this case, it's going to loop over 100 instructions 100 times with the specific dependency distance that I want. I then define my specific passes. So in this case, I have 4 passes. The first one creates all of the instructions, or creates a building block of instructions. Then I go and then I emit random instructions within that. I reserve specific registers. And finally, I allocate the registers based on the dependency distance that I care about. In this case, I'm sweeping over the instructions as well as the dependency distance. And then finally, then I go and then I emit this and throw this off into some directory and from there. So now that then I actually run my program, then I go and I generate all of my different benchmarks with different dependency distances, and then I can go and run them on the Rocket chip emulator. So what you can get out of this is then, oh, okay, so for my adds, multiplies, and divides, these have a certain behavior. Specifically, you'll notice then, of course, add, this is running through the ALU, so it's going to have a latency of 1, throughput of 1. The floating point unit is pipeline, so you're going to see sort of this linear increase. And the multiplier and the divider, well, they're multi-cycle implementations, so they're basically, they don't have any effect based on dependency distance. And then going for that, just to concretize that, then I can effectively then infer exactly what the internals of Rocket chip look like. So in this sense, what it's then allowing you to do is then, again, as a verification engineer, you can then go in and then very quickly, sort of what I would argue with about 4 lines of Python, come up with enough tests to then try and answer these types of questions. So roughly what the takeaways which I would argue for this sort of as a user of Microprobe myself in order to get this stuff up and running, really what you should do is you should be writing microbenchmark generators and not actually writing the benchmarks yourself. And I'll sort of go even a further step is that you should be writing passes for Microprobe as opposed to even going through and writing the microbenchmark generators. So as I mentioned, this is currently held up in sort of legal review internal to IBM. But if you'd like to have some early access or something like that, feel free to shoot me an email or shoot Ramon an email, and we can try and get something set up. Otherwise, when I get back to IBM, I'll go and try and push hard on this and get this pushed through so that this can actually be out and useful for people who are building RISC-V implementations like many of you out in the audience. And just finally, I just have to then mention that this was supported by the DARPA Perfect program, through which sort of I've been then funded to then be able to work on this. And that's it, and I'll yield the remainder of my time.